from the last weekly contest, adjacent increasing subarrays detection part 1. We are given the number and we are given k, and we want to find two adjacent subarrays of length at least k such that both the subarrays are increasing, strictly increasing, right? Not at least of length k, but exactly of length k, right? And we just need to return if it is possible or not. Well, there are a couple of ways to solve this problem. We can do O of n square since the constraints are pretty small. But what came to my mind for the first instance, like right away, I thought I should uh, iterate from the right side and create an array which will tell the longest for every number it will tell the longest length or the largest length which is strictly increasing and store it in that particular array, and then we can use that particular array to basically check if for every number at suppose the new array of I is greater than or equal to k, and the new array of I plus k is also greater than or equal to k. In that case, I should return true, right? And I'll do that for every number from 0 to n minus k, right? Or n minus k right here. And beyond that, I don't need to check, right? Because uh, it's not possible because the other array, the other adjacent array starting point will become out of bound, right? So basically, a couple of ways to solve this problem. I am showing what came to my mind first. Right, let's get the size in n and create the new array. Uh, let's name it dp since it's kind of a dp. Initialize it with value 1 because for every number we can have at least one length of increasing subarray, and start from the uh, yeah, start from n minus 2 because we know that n minus 1 will be 1. For n minus 1, the dp value will be 1 because beyond that there is no other value. And while I is greater than or equal to 0, and if nums of I is less than nums of I plus 1, in that case it is increasing. So let's have dp of I is equal to dp of I plus 1, and that's it. Uh, I is equal to 0 while less than n minus k. So I'm traversing only till the point it makes sense to traverse. And for every element, let's check if dp of I is greater than or equal to k. So this alone can form the required strictly increasing array, and the dp of I plus k is also able to make that. In that case, return true, else return false. Wait, let's see if this works. dp of I is greater than or equal to dp of I plus k is greater than, oh my bad. Let's see now. Let's submit it. So this is a very similar problem. Part 2, we are given nums and we are not given k, and we need to find the maximum possible value of k. So we can just do the same exact thing, but now at this point we will just check if we are able to form increasing size of I plus I. Basically, uh, I'm going to do the same exact thing. So let me copy the code. Alright, here this particular point will be exactly same, just that here instead of returning true, I am going through the entire array, right? There can be two cases if we look at it carefully. One case can be that the entire array or the entire array is kind of strictly increasing, right? So 2, 3, 4, 5, 6, 7, 8, 9, right? So here 1, 2, 3, 4, 5, 6, 7, 8. 8 is the longest length for this particular value. And there is no adjacent array that we can form if we look at this entire array in itself as strictly increasing. So if for a particular value we are looking at the entire subarray as the only strictly increasing array, that is wrong, because we can obviously divide it into two parts, right? So this can be a possibility, and I have to take care of this for every element, right? And the second possibility is we have something like this, 589, right? So here it will be something like 345,589. So 3 will be the answer if I'm not wrong, because this is not strictly increasing. So this and this should be giving k as 3. That's the maximum that I can get. So what I'm essentially doing is I am basically having an answer variable, and first I am updating it for the case where answer is equal to dp of I by 2, right? So that will give me, even for odd cases, this will be true. Suppose this was the 1, 2, 3, 4, 5, 6. Suppose this was it, right? So this is the odd case, and we can still divide it into two halves. So 2 will be the maximum k. If that is not true, then I will check first if dp of I plus I, that's the maximum that I can. If I consider this entire length inside dp of I as one array, then the adjacent array will start at dp of I plus I, and I should make sure that this does not overflow or become out of bound. If it is within bounds, then I will consider my answer to be maximum of this, or uh, whatever the minimum value will be, right, of the two adjacent subarrays that I'm talking about, right? One is this subarray, dp of I plus I, uh, about a dp of I is one subarray, or dp of I plus I, this will be the index of this adjacent subarray, and what will be its value? dp of whatever the index is. So this, out of the two, I want the minimum of the two, right? So this will be my answer, right? And I'm going to return answer instead. Let's see if this works. All right, this works. Right, so the third problem from the last weekly contest, sum of good subsequences. A good subsequence definition is a array or a subsequence in which any two consecutive elements have a absolute difference of exactly one. That's a good subsequence. And we are given an array and we are asked to find all possible good subsequence sum, right? So sum of all possible good subsequences is what we require. So if we look at the first example, here we are given 1 to 1, and suppose I am at 1. So if I am at 1 and I want to find all the good subsequence that ends with 1, with this particular number, then I will look for the past where either I have a subsequence ending with 2 or I have a subsequence ending with 0, right? Because that is the only way I can have a consecutive difference of 1, absolute difference of 1. So I don't have anything in the past. And by the way, I'm looking for that key whose value will contain the sum of all the possible good subsequences ending with 3 or ending with 0, right? So the value is where I should have the sum so that I can build upon that, right? In a DP kind of manner. So if at this point I don't have anything, then I will put this inside something called probably a map where the key is 1, and I have a sum of only 1, right? Because with 1 as the only value in a subsequence, I can have a sum of only 1, right? So that's it. The second thing I need, because we are looking for a subsequence, right? So there can be multiple ones in the past. And for each one, I should add a 2 to it, right? Or for each one, or for each 2 or 0, I should have a 1 to it. So what I'm saying is, for 1 in the past, I'm looking for 0 and 3, oh sorry, 0 and 2, and that can be multiple, right? There can be multiple zeros, there can be multiple twos with their own sums. So in that case, I should have a frequency count as well for that. So right now there is only one, so that's it. Now if I move forward, I see I have a 2. So in the past I look for a key 3 or 1, right? I don't have 3, but I have 1. So if I have 1 and its sum is 1 and its frequency is 1, right? So, well, I can only add to its sum one time, right? I can only add 2 to this sum one time because there is only one frequency. So I'm basically saying sum plus frequency into the current value, right? Which is nothing but 1 plus 1 into current value, that is 2. So that will give me a value of 3, which is nothing but 2 in itself and 1 comma 2. This basically represents the total possible sum that of good subsequences ending with 2, right? So that's what we are doing. And if I move for now that I have 2, I will also add that in the map so that the future values can find it in the past. The value, some value will be 3 and the uh, frequency will be 1, right? And the last thing is we will keep doing this for the future values. Last thing is we'll also keep adding sum. We'll have a running sum that will be our answer, right? Because for example 1 2 was the numbers array, right? So here if I follow the rule and get the answer, then that will be just 1 2 1 2. That's it. That's all I can have, and the total sum will be 1 plus 2 plus 3, that is 6, which is nothing but uh, so if I keep a running sum, suppose this was not there, I'll have a running sum, right? So I'll have an answer where I will add 1 to it, then I will encounter 2 for whatever value that I've encountered, I'll add it to my answer first, and then I will add the 3 that I have found, right? And that will give me my answer, right? So I can have a map where I can have a sum and a frequency, and I can build upon that and have a running sum that will be my answer. So let's have that. Uh, since I will, I'll have a map which will have a key and a sum and a frequency as a value. So I can have a pair which will be like this. I will have an answer which will be my running sum. I will have a iterator which will iterate over nums, and for each n I am looking for the lower limit which is n minus 1 and the upper limit which is n plus 1 in the past. If uh, I do find map inside my map, I do find the lower limit, then uh, let's have a variable called count, and since it can have a large value, let's have, or probably we are going to mod it anyway, so let's have integer only, initially 0, and for each number n I am going to calculate its sum, right? So let's have a current total. Current total will right away have n in itself because n alone can form a subsequence which is valid no matter what its value is. And on top of that, this current total will also have uh, that's equal to the sum of L, that is MP of L first, plus the frequency, that is NP of L second, into whatever the value right now, N, right? That's it. And on top of that, I should keep building the frequency as well, right? So now that I have, suppose in this example, I am at 2. So I'm going to increase the count of 2, right? So that will be 1. Sorry, 1. So that frequency will be count. So if I have found NP of L, that means I'm going to use N once. So I am going to increase its frequency uh, by how many times? Well, the number of times I've used it. So I've used it this many times. So I'm going to increase it this many times, right? So I'm going to do the same thing for U as well. That's it. So I'll also have a running sum, which will be my answer at the end. So answer plus equal to current total, and finally I'm going to add it to the map. But if I already have a 2 present in the past, right? So that means I already have a sum and a count, right? So in that case, I should add the current total to that particular value, right? So basically I can have a current count already to 1 because I'm going to use this alone itself, right? So I'll have 1 already here, and finally I'm going to add this. Uh, so if inside map I already have n, then I'm thinking about it. I should have it. Should I check if it is already present or should I not? I think I should not. Probably, let's see. If NP of n is equal to current total plus NP of n, whatever the value is previously, and the same thing goes for the MP of n second plus count, or let me write it like this: count plus MP of n second. I'm not really sure what will be the default value of a pair. If that is the case, then I can just divide it. Let's see what happens. Let's return. I should do a mod for everything, so let's have a mod as well. Okay, MP of first. Oh, this should not be arrow, by the way. This should be a dot. This should be a dot. This should be a dot. 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 Okay, let's have a mod here. 1E9 plus 7, and there are a lot of places where we have to mod. So let's put a long here so that this doesn't overflow, and then let's do a mod here. Let's do a mod here as well. Let's copy this instead and then change it here so that I don't need to update a lot of things. MP of u, MP of u. That's it. And I think here it might overflow. So mod, mod, and finally mod. Let's see now. Alright, this works. Well, yeah. So since this is a map, I'm basically doing a O of n in terms of space and probably a O of n on uh, the time as well because it's an unordered map, not a map. And yeah, that's the third problem. The fourth problem from the last weekly contest: count k reducible numbers less than n. So we are given a string which represents a binary format number, and we are asked to find uh, let's see, return an integer denoting the number of positive numbers. So we are asked to find all such integers which are less than the given integer, such that they are less than n and also k reducible, which basically has a definition: k reducible, where if an integer x is said to be k reducible if we replace x with the count of set bits in its binary representation, and we keep doing it until it reduces to 1, right? So if we have 6, 6 becomes 2 because it has 2 set bits. 2 is basically 1 0 in its binary form, which has 1, so it reduces to 1, and that's it. That's it. We need to return the number of positive integers which are k reducible, right? So this seems like a DP problem, isn't it? Because we have a S or we have a string which is in the binary format, and we want to generate basically all the numbers that are less than the given number, and we need to find if they are k reducible or not. Let's look at the constraint. There are only 800 of them. So instead of finding the k reducible thing during the DP, we can just do that uh, beforehand for all the 800 numbers and store it, recompute it, so that when we generate during DP this particular number, at that point of time we can just look at that pre-stored value and see if it's k reducible or not. That's it. That's the first thing. The second thing is, how are we going to generate it? Well, if I have 1 1 1, I'm going to start from 0, right? And I'm going to generate all the numbers that are less than the given number, right? So if I have 1 1 1 and I start from 0, then I can put a 1 here, or I can put a 0 here, which I already have, right? And then move forward. So in that case, I have two uh, decisions, right? Two things that I have. So the first thing is 0. At this point, does the prefix of the original number or the limit, is it matching? If it is not matching, then all the numbers after that are going to be less. right? That's the first thing. That's the first point. If the prefix is not matching, if prefix does not match, then all the numbers that are going to be generated forward from here are are going to be smaller. Alright. And the second decision or second thing is if I have a 1, that means the prefix is matching, right? So in that case, uh, I should put a 0 or a 1. If I put a 0, then then prefix at this point prefix matches. That's the first thing. If I put a 0, then prefix becomes false. It is not matching. Prefix match is now not matching. That means from here on forward, this becomes basically this, right? So all the numbers from here are going to be lesser. But if I put a 1, then I keep prefix match uh, true, right? So that's about it. That's basically it. We're going to have we're going to have prefix match as a state, and we are going to make decisions. So if it is 0 and the current bit is not 0, that means it is not matching, then the prefix match is false. That means all the numbers from here are going to be 0. So I mean all the numbers from here are going to be lesser than the limit. So here at this point I can put a 0 or a 1, it doesn't matter. The prefix match is always false. Instead of 0, I should mention that case where current bit does not match uh, 0 or does not match 1, right? That is what we have. So if it is matching, in that case I will have a prefix match condition to be checked. Otherwise, if it is not matching, then in all the cases I'm going to have a prefix match to be false. That's it. And the last thing is we are also going to have to count the set bits, right, every time, so that I can use the pre-computed value to find if that number is key reducible or not. So basically the first thing I'm going to do is have a vector in which I'm going to store if this particular number is key reducible or not. So let's define it outside so that I don't need to pass it inside the DP function. And let's resize it to the constraint value to particularly 801. That is fine. And how am I going to find it? If a particular number is key reducible or not, I'm going to iterate through all the numbers. First, I'm going to check what is its total length for this particular number. If that exceeds k, that means it is not key reducible. So we are given a integer k as well. I just forgot about it. So k reducible means in these many operations, am I able to make a particular number reduced down to 1 or not, right? So I'll keep count of the length, the number of operations that I've applied. Let's name it operations, and I will have a n which is pointing to the number. So while n is greater than 1 and length is less than k, I'll keep reducing it. That means I'm going to find the set bits for this particular number, which is initially the count is 0. Let me have a temporary copy of this number so that I can modify it. So while 10 is greater than 0, I will check if 10 and 1. If that is there, then count must increase. Now I can just divide this by 2 and lose my last bit or the least significant bit. At this point, I will check or so I have reduced down. I should increase my operations first since I have performed one operation, and I should, since now I've reduced it to count, my n, my count will become my new n, right? Because 6 is reduced to 2, now 2 becomes the number that needs to be reduced, right? So n is equal to count, and that's it. At this point, I will see k, I'll update k reducible of this particular number to be 1 if length is less than k. So if length is less than k, I am going to have 1 here, otherwise I am going to have 0 here, right? So I have the pre-computed value. Now I'm just going to call the dp function, in which the first thing will be the index for this particular string. Second thing is going to be the set bits count rate, that will be 0 initially, and the third thing is going to be uh, if the prefix is matching or not. Initially I'll keep it a match, and that's how our dp function is going to be. So initially also I need to pass the string as well. So string passed by reference index set bits count is prefix match. So if the base case, if the I mean the base case will be if index is equal to s dot length, right? So at this point, I should return 1 or 0. 1 I will return only in scenarios where the prefix is matching, and or if the prefix is not matching, that means it is k reduce, that means it's smaller than the limit, right? So if prefix is false, then all the numbers that I have is going to be smaller than the limit, and that's what we want. We want it to be strictly less than n, less than n, right? So it's not even going to be equal. So if prefix match is prefix match is false, that means if it is a smaller value than n, and if it's k reducible, is k reducible, which is nothing but the set bits count. Whatever the set bits count is, that's the value. If they both are true, then return 1, else return 0, right? Or I can just do this, have just a single line returning this, because if it is true, then it will be 1 in itself. Now comes the part where we need to either append a 1 or a 0, right? So if prefix is not matching, that means if the prefix matches, or if it's matching, suppose, that means I can put a 1 or a 0. If I put a 1, then if the current bit is 1, then what to put 1 or 0. Similarly, if it is 0, then what to put 1 or 0. And the same thing is going to be here, right? So if prefix is matching and the current index or the current bit is 1, that means if I put a 1 in the next, if I put a 1 appending to this, then I am going to keep having the prefix match to be true, right? Because the current bit itself is true, or 1. So let me add this particular part to the answer. S will be S, index will increase by 1, set bit count will also increase because I'm appending a 1 to it, right? And the prefix will be true, and that's pretty much it. Now if you put a 0, then I am not increasing the set bit count, and the prefix will be false here because the prefix is not matching because the current bit is 1 and I'm putting a 0. Similarly, if I put a 1 here, that means the last bit was 0. I can't put a 1 here because I am going to increase the number above the limit if I put a 1 here, right? Because the current bit is 0 and the prefix is matching. That means the number is equal if I put a 0 here. If it is 1, then I am going to increase it above the limit, so 1 is not possible. So I am going to only have this. Uh, yeah, set bit count will not increase, but I'll still have this as true because S of index is 0 here and I'm appending a 0, right? The next thing is here. At this point, prefix is not matching. So if prefix is not matching, then whatever the case is, I can put a 1 or a 0, whatever the case is. So I don't even need to check if prefix is not matching, then the number is going to be smaller irrespective of 1 or a 0. Got it? So let's have this paste here. Uh, this will stay false and this will stay false, and that's pretty much it. Let's return here. We need to minimize it. Let's see if this works. So I don't have a length, I have operations. Let's be careful and update it. Oh, so there is the operations is k reducible. Oh, the spelling is wrong. Reduced. Okay, operations is less than k. I'm having some issues. I should not have this equal. Okay, let's minimize it. We have three states. I can have a cache which I can define above so that I don't need to pass it in the DP function. A 3D DP. The first thing will be the index, which will be of size. Uh, let's resize it here. So the first thing is s dot length plus one vector of vector of int. This will be again s dot length plus one because set bits count can be something all ones, right? So that will be of length s dot length plus one, comma vector of int 2 comma minus 1 because it can be either 0 or 1 is prefix match and initial value is minus 1. So if cache of s, index set bits count and is prefix match if they are not equal to minus 1, then we return, and here let's put this. And do we need to mod it? Yes, I think we need to mod it. So let's have a mod 1e9 plus 7. Let's do a mod here. Let's do a mod here. Let's do a mod here. And let's do a mod here. Finally, that's it. Let's see if this works. Okay, let's define it outside. Oh, okay. Oh, not equal to minus 1, I'm right. Okay, let's submit it. Okay, it works. That's the fourth problem. If we talk about the time complexity, index, set bits count will make it O of n square, and space will also be O of n square, right? Thanks.